So we stop here. One of the tricky problems for a TCP NAT is handling peer-to-peer applications operating on host residing on the private side of multiple NATs. Some of these applications use a simultaneous open. Sorry, I just want to clarify here. RFC 5382, a product of the Behave working group, notes that a TCP connection can be configured to send keep alive packets. See chapter 17, and the default rate is 1 packet every 2 hours, if enabled. Otherwise, a TCP connection can remain established indefinitely. While a connection is being set up or cleared, however, the maximum idle time is 4 minutes. Consequently, RFC 5382 requires Rec 5 that a NAT was at least 2 hours and 4 minutes before concluding that an established connection is dead, and at least 4 minutes before concluding that a partially opened or closed connection is dead. So this is the ideal, but this is not actually the what most use today, or what the provider actually use. So they actually do not wait for 2 hours because they have limited memory, and they only keep that for 15 to 30 minutes, and if they don't see any acknowledgement for that TCP connection, they will terminate it. Additionally, TCP is still the previous one we've mentioned, or in the previous video, the TCP SYN-ACK or the three-way handshake are still the most prevalent way to do TCP. It still constitutes a lot of part of the internet, but for commonly used apps today, they slowly transitioning to UDP or to QUIC. So those UDP doesn't need handshake. That's why it's fast. It has this outgoing refresh rule, which allows the NAT to refresh it in its NAT. So UDP actually delete the session in memory within 30 to 60 seconds of not sending packet. Later we will gonna discuss that further, but we just need that to give context on how important this NAT with respect to our overall goal. So let's see. Let's try to discuss what QUIC means overall, and how NAT actually is being used now in the internet. So if fragments after the first fragment do not contain transport layer info, UDP or TCP ports, because NAT or NAPT needs ports to translate connections, it cannot translate fragments properly. Why? A NAT needs these fields to do its job: source IP, source port, destination port. But only fragment number 1 contains the TCP or UDP header that includes port. Fragment 2 and 3 contain just raw payload, not ports. So a simple NAT cannot know which internal device to deliver fragment number 2 to, which NAT translation mapping to use. Real-world behavior. Why consumers almost never see fragmentation today? This is the part because 80% of the consumer traffic. So in modern consumer networks like home Wi-Fi, prepaid hotspot, Mobile data fragmentation is rare because path MTU discovery PMTUD is used by most modern apps. TCP automatically avoids fragmentation. CDN plus video platforms optimize packet sizes. Mobile carriers block or rewrite DFB to avoid fragmentation issues. Routers often just drop fragments beyond number 1 because NAT can't handle them. Result, 95 to 99% of all traffic from mobile and home routers is non-fragmented. Consumers basically never hit fragmentation today. This is why most NATs survive with simple rules. Let's see how the TCP actually work. So 80% of real-world NAT behavior is the simplified TCP logic. So 80% of its traffic is the simplified TCP logic we discussed in the previous video, not the ideal, which sent packets every 2 hours and another 4 minutes for partially open. So because the routers does not have that huge memory, meaning NAT watches for outgoing TCP SYN. If SYN no ACK, delete quickly. If SYN ACK, treat it as established and keep a long timeout. NAT does not wait 2 hours and 4 minutes unless it's high-end equipment. Home routers use shorter timeouts, minutes, not hours. CGNAT uses even shorter timeouts, 30 minutes, even 5 minutes. RFC 5382 is the ideal standard. The simplified TCP state behavior is the real-world practice. This is the 80 or to 20 rule. Why NATs don't follow RFC 5382 perfectly? RFC 5382 says keep established TCP mappings alive for greater than or equal 2 hours and 4 minutes. Keep half open for 4 minutes. Half open is when it sent SYN packet or when it send a FIN packet, or if it's receive an ACK from the server. But the real-world NATs, especially cheap routers plus CGNAT, do not do this. They have limited RAM, must store millions of mappings, need to recycle ports quickly. They cannot afford 2-hour timers, so they shorten the values. Real-world NAT behavior, 80%. Home routers, PLDT or home Wi-Fi or Globe prepaid routers, TCP established timeout 10 to 30 minutes, half open 30 to 60 seconds, UDP port timeout 30 to 60 seconds. Converge CGNAT, your case, TCP established timeout 5 to 20 minutes, half open 30 seconds. UDP port timeout 20 to 30 seconds, very short. This is why WebRTC goes into turn fallback, games into strict NAT, SSH or VPN, random disconnections, WebSockets reconnects. For yeah, that's the reason. But modern router has this refresh for outgoing for UDP. That's why they were able to still keep the TCP and the UDP for SSH and VPN and for WebRTC. So the simplified TCP logic, this is the real world. NAT watches outgoing SYN. If SYN gets no ACK, mapping remove fast. If SYN gets ACK, mapping treated as established. NAT may prove the connection. NAT resets timeout if it sees any ACK. This is how 80% of the NATs actually behave today. RFC 5382 is just ideal. It's only for high-end enterprise firewalls like Cisco or Fortinet. So the simplified TCP logic is the real world behavior. The RFC 5382 is more like the 20% of that TCP behavior. So what actually happens for 80% of Filipinos on home Wi-Fi? Most common app usage for browsing TCP 80 over 443 uses simplified NAT behavior. For YouTube, Netflix, TCP over quick or NAT holds mapping 10 to 30 minutes. Messenger or Telegram WebSocket TCP depends on NAT timeout. Games UDP mappings expire fast. TrickNAT, VoIP, WebRTC, UDP mappings expires. Third fallback. The simplified model governs all of this. Why this matter to you? Because your converged CGNAT uses very short UDP timeouts, non-RFC compliant TCP behavior, minimal NAT state tracking, no long-lived TCP protection. So WebRTC often fails to turn. Game shows TrickNAT, some website disconnects, SSH resets. LiveKit P2P rarely works. Scene-based logic dominates. RFC timeouts are ignored. Real-world numbers, percentage of the internet endpoints behind NAT, 70 to 75 globally. Percentage of the endpoints behind CGNAT, 40% for mobile, 20 to 30% using broadband. Converge, 50 to 60% use CGNAT. So percentage of NATs following simplified TCP state logic, 80%. Percentage following RFC 5382 strictly. So let's now go to Quick. So I want to discuss Quick. So what does the normal protocol that is actually being used in the internet? Is it really UDP or TCP? So does YouTube use TCP or UDP? Answer both, but mostly UDP via Quick. Protocol Quick UDP usage, 95% of YouTube video delivery today. TCP HTTPS, 5% fallback for old devices, old browsers, block UDP. YouTube pioneered Quick, now standardized as HTTP3. Service by service breakdown, TCP or UDP. So here's the accurate table. Service, YouTube. Transport, mostly UDP, Quick. Explanation, video segments over HTTP3. Service, Facebook. Transport, UDP plus TCP. Explanation, app uses Quick. For content feeds, messages via MQ on TCP. TikTok, transport UDP Quick. Explanation, uses HTTP 3 aggressively for video delivery. Chrome browsing websites, UDP Quick and TCP. Explanation depends on website. 40 to 70% of web now uses Quick. So most of the web now in Google Chrome, when you browse, are actually using Quick or HTTP 3 port. Instagram, UDP plus TCP. Reels are loaded via Quick or UDP. API calls via HTTPS or TCP. Messenger, WhatsApp, Viber, transport TCP for messages, UDP for voice or video. So as you can see, they have two protocols in one apps. For signaling, it's equals to TCP or for messages. Media is for UDP. Spotify, transport, TCP mostly. Explanation, audio streaming over HTTPS. No Quick yet for most users. For Spotify, we mostly use TCP. Shopee or Lazada, transport, TCP. Explanation, e-commerce apps use classic HTTPS APIs. Mobile games, transport, UDP. Explanation, real-time games use UDP. Some use proprietary protocols on UDP. Percentage breakdown, HTTP2 versus Quick. HTTP 3. So across the internet, 2024 to 2025 measurements, protocol, HTTP 3, quick over UDP global, percentage 35 to 45%. In the Philippines, 40 to 50% PH is quick heavy due to mobile use. HTTP 2, TCP, global percentage 45 to 55%. In the Philippines, 40 to 50%. HTTP 1.1 still TCP global 5 to 10%. In the Philippines, 10 to 15%. So why PH says more quick? Consumers use mobile data more. Carriers optimize for UDP-based flows, faster handshake. So for mobile data, our carriers PLDT Globe are optimized for faster handshake or quick. So we still use TCP, but it is changing now. YouTube, TikTok, FB dominate PH traffic. They push quick. But just in case that you're not still use TCP, such as for Spotify, they actually use that basic handshake, and they delete fast those NAT session. Why quick or UDP avoids fragmentation? Since your earlier question was about these, quick packets are usually 1200 bytes max. Fits safe MTU across mobile plus Fiverr plus CGNAT. It avoids IP fragmentation entirely. Works even behind restrictive CGNAT like Converge, mobile or Wi-Fi routers. This connects directly to MTU, PMTUD, and NAT questions. Application layer data format used by each major app. Most apps use a mix of JSON, protobuf, binary frames, and compressed payloads. Here's the breakdown. Service, YouTube, data format, binary plus protobuf plus MP4 segments. Explanation. Video chunks delivered via Dash or VP9 in binary. Facebook, data format JSON plus binary plus compressed strip. Explanation. Feed equal JSON, media equal binary. TikTok, data format binary plus protobuf like formats. Explanation. Extremely optimized for size. Chrome websites, data format HTML, JSON, JPEG, or WebP JS bundles. Explanation varies by websites. Instagram, JSON, API plus binary images or videos. Explanation, all media is binary. Messenger or WhatsApp, data format protobuf like binary. Explanation, messages are compact binary blobs. Spotify, data format OGG/Vorbis binary plus JSON API metadata. Explanation, songs equal pure binary streams. Shopee or Lazada, data format JSON APIs plus JPEG/WebP images. Explanation, lightweight API calls. Mobile games, data format custom binary protocols. Explanation, real-time tick data in binary. Important, only very early layers use ASC2 or HTTP headers. Actual app content is binary, compressed or structured formats. So putting it all together in percentage, here's the real-world consumer internet usage. Traffic by volume category: video streaming, YT, TikTok, FB video, Netflix. Percentage of bandwidth in PH, 70 to 80%. Transport, mostly quick UDP. So most of the internet actually do video streaming, and the next is social media and browsing, then games and messaging. So for social media, we have 10 to 15% of bandwidth. It is mix of quick or UDP plus TCP. Browsing, 5 to 10%. Transport, still mix of TCP and UDP. Games, 1 to 3%. Transport, mostly UDP. Messaging, less than 1%. Transport, TCP for text, UDP for calls. So final summary, Most consumer traffic today, 60 to 80%, uses UDP via quick HTTP3. TCP is still heavily used for API calls, browsing, and messaging. Streaming apps use binary media formats, not ASC2. Fragmentation is almost non-existent because quick or TCP use PMTUD plus 1 to 100 byte packets. PH networks converge GlobeSmart push more quick than Western networks due to mobile heavy usage. So UDP is blind to NOT, no SYN, FIN, or RST bit. TCP equals has SYN, FIN, RST. So a NOT can detect connection started, SYN, connection active, packets, connection closed, FIN, or RST. So NOT knows when to create and delete a mapping. UDP has none of that. UDP packets are stateless. No handshake, no connection close, no indication that two endpoints are related, no session lifetime info. So NOT cannot know when a UDP session starts or stops. This directly explains the text you posted. Part 2. How NOT tracks UDP even without SYN or FIN. Because UDP has no state markers, NOT creates a temporary mapping. Like this, internal colon 192.168.1.10 colon 4000, external 161.49.12.7 colon 6021 CG NOT. But NOT must delete this entry if unused. So NOT vendors invented a timer. UDP NOT mapping timeout. RFC requires greater than or equal to 2 minutes. Recommended 5 minutes. This means if no UDP packet flows for 2 to 5 minutes, NOT deletes the mapping for UDP. Part 3. Why this relates to directly to Quick. Quick equals Google or YouTube transport layer built on UDP. Quick is a connection, but NOT doesn't see it as a connection because it's UDP. So Quick does this. So Quick is actually a connection, but NOT doesn't see it as Quick because it's UDP. Quick does this in user space. Quick sends periodic keep alive packets. Why? To keep NOT mapping alive. If the NOT deletes the mapping, your YouTube stream dies. This is why Quick was assigned around NOT limitations. It includes keep alive frames, packet numbering, loss detection, anti-timeout behavior, all to survive NOT behavior from the text that we discussed. So how this connects to stun, turn, and ice we discussed in the previous video. Why does WebRTC need stun or turn or ice if Quick already used UDP? Because Quick is silent, server, client to server, but WebRTC is peer-to-peer. Your router has NOT. Your ISP Converge Globe has CG NOT. So peer-to-peer would fail unless you know your external NOT mapping. Stun, you open a NOT hole, UDP hole punching. If hole punching fails, turn relay. ICE decides the best path. How they relate to NOT that we have discussed. UDP has no 4-tuple base connection state, just like the tables that is being created per session are not mapping for SYN bit, FIN bit, acknowledgement, etc. This makes WebRTC not traversal hard. Stun and ice exist to fix this. Then, NOT uses a mapping timer. Stun candidates must be used before the timer expires. Otherwise, NOT deletes the mapping. ICE candidate becomes useless. Turn is needed. Not outbound refresh versus inbound refresh. Many PH ISPs Converge only support outbound refresh. They do not support inbound refresh where the connection or the will keep alive if they notice an outbound request, meaning your outgoing UDP keeps not alive. Peer incoming's UDP may not refresh the timer. That is exactly why hole punching often fails, forcing turn relay. How quick relates to stun or ice? Many think quick and stun or ice are unrelated, but here's the deep truth. Quick is equal UDP but reliable for client to server. YouTube, TikTok, Facebook use it. Stun ice turn equal UDP but not friendly for peer-to-peer. WebRTC, games, Zoom use it. Both solve problems that UDP not behavior is unpredictable. Part 6. Fragmentation relates directly to quick stun turn. Your text says, or the previous discussion says, IP fragments other than the first do not contain port numbers. So simple NATs cannot handle them. So if you send a large UDP packet, it gets fragmented. NAT cannot map fragments after the first packet loss, stun or turn fails, quick fails. Quick uses MTU discovery to stay under 1200 bytes, so packets never fragment. Stun also uses small packets to avoid fragmentation. Turn relays packet also tuned to small sizes to avoid fragmentation in CGNAT heavy countries like Philippines. So how quick stun, turn, ice relate to UDP NAT behavior? So we have UDP NAT, no SYN or FIN or RST. It is connected done to it the quick or HTTP3, which is the client to server apps, which has keep alives, anti-timeout logic, MTU limited packets. For the other trunk, we have stun or ice or turn peer-to-peer apps, which discover external IP report, hole punching, turn fallback. Both are solving the same underlying problem. UDP plus NAT is unstable because there is no state, no SYN and timer expires. So the summary, UDP has no connection markers, NAT guesses the session lifetime. Quick and stun or turn both need keep alives. UDP fragmentation breaks NAT. Quick, stun, turn use small packets. UDP NAT timeout kills sessions. Quick uses timers, stun uses refresh, some NAT support outbound refresh only. Hole punching often fails. ICE decides direct UDP or relay turn. This is exactly why YouTube works through quick, WebRTC sometimes needs turn, game struggle under CGNAT, converge often break peer-to-peer UDP. So are YouTube, TikTok, Facebook, video, Netflix client to server? Yes. All major streaming platforms, YouTube, TikTok, Netflix, Facebook, are client to server, never peer-to-peer. Why? Legal licensing reasons, bandwidth consistency, CD and delivery, predictable quality, privacy, or security. So even if they run UDP, it is UDP based quick in a client to server model, not P2P. Why they use quick or UDP? Quick gives low latency than TCP, faster connection setup, 0 to RTT, TLs built in, loss recovery without head of line blocking, not friendly, keep alives. This is why Google, YouTube, Chrome, Android uses it. Quick and NAT. How does quick stay alive? This is the part connected to NAT plus UDP plus timers. NAT refresh basics. A NAT holds mapping like this. Internal IP colon port to public IP colon port. For UDP, NAT has no handshake, so it does this. If no packet is seen for X seconds, NAT deletes mapping. RFC 4787 recommends minimum 2 minutes, suggested 5 minutes. This is why UDP apps must send keep alives. How Quick solves NAT timeout? Quick implements its own keep alive logic because it knows NAT timeouts are short, 30 to 120 seconds. It knows UDP has no connection state. Quick sends very small packets. Quick keep alive frames. Ping frame 1 byte plus minimal overhead. Act only packets, padding packets to prove MTU. These frames refresh NAT. Client to NAT to server. A quick server like YouTube CDN. Edge node also send pings, ACKs, path validation packets. As long as some packet crosses NAT every 20 to 30 seconds, the NAT mapping survives. This is what connects quick. NAT refresh requirement from RFC 4787. Quick is not stun or turn or ice. Huge difference. Quick is not equal hole punching. Quick uses UDP but does not do NAT traversal for peer-to-peer. Stun or turn or ice are only for WebRTC, P2P calls, VoIP, some multiplayer games. Streaming services do not need NAT traversal because the server has a public IP. Relationship, protocol, quick, purpose, client-to-server transport used by YouTube, Chrome, TikTok. Does it need stun, turn, or ice? No. Protocol, UDP, purpose, low-level transport used by games, quick, WebRTC. Needs stun, turn, or ice? No. Protocol, stun, or turn, or ice. Purpose, P2P, not traversal, used by WebRTC. VoIP, needs stun, turn, or ice? Yes. So quick, keep NAT mapping alive. Stun or ice creates a new NAT mapping to reach peer. Completely different. How quick handles MTU, very important and misunderstood. Quick enforces PMTUD, path MTU discovery. Typical MTU, Ethernet 1500 bytes. Quick maximum packet size 1350 bytes. Why 1350? Because IP header 20 to 40 bytes, UDP header 8 bytes. Quick overhead varies 25 bytes. Quick packet must fit without fragmentation. NATs cannot reassemble fragment easily. We have seen that on the screenshot. Quick purposely send packets below MTU to avoid IP fragmentation. This makes Quick much more NAT friendly than raw UDP. Quick versus TCP keep alives. Core design difference. TCP has handshake, SYN to SYN ACK, then ACK. It has state in night. Idle TCP timeout is typically 2 hours, RFC 1122. TCP keep alive defaults 2 hours, 75-second retries, 10 probes. 10 probes. TCP is not designed for NATs, not games decade later. Quick, no handshake at IP level, TL's handshake inside Quick. It runs over UDP, not deletes mapping quickly, must send frequent keep alives 20 to 30 seconds. So this is how Quick send alives because most router delete UDP after 60 to 2 minutes, 60 seconds to 2 minutes. Quick always send keep alives during 20 to 30 seconds. It detects path issues, fast, PTO, loss detection. It avoids fragmentation with PMTU, less than 1500 rules. TCP is slow and conservative. Quick is aggressive and adaptive. How Quick is implemented in OS or code? Quick libraries like Quish, MS Quick, and GTCP2 do the following. It binds a UDP socket. So a lot of these are written using low-level language which allows them to connect quickly to their hardware that makes the browsing fast. It sets socket options, DSCP, pacing, GRO/GSO. It maintains per connection timers, handshake, idle timeout, path validation, PMTUD, retransmission, PTO. It sends periodic keep alives, manage congestion control, BBR, cubic. The OS simply sends or receives UDP packets. No understanding of quick connections. Everything else is a user space logic. Final summary. How quick NAT MTU keep alives are connected. Quick over UDP. Must satisfy NAT outbound refresh. Send keep alives 20 to 30 seconds. Uses packet sizes less than MTU 13550 bytes. Avoids IP fragmentation because NATs cannot handle fragmented UDP well. Client to server only, no P2P. Has built-in loss recovery, Pacing, congestion control, replaces TCP plus TLS plus HTTP over 2 with a single protocol. TCP, not idle timeout is long. Keep alive is slow, 2 hours. No control over MTU beyond PMTUD. Kernel handles everything. User space up, have less flexibility. So front-end frameworks, React, Angular, Next.js do not implement control or interact with Quick at all. Not even 1%, not even directly. They cannot bind UDP sockets, control Quick handshake, set idle timeout, run PMTUD, send retransmission, PTO, adjust congestion control, because browsers do not expose any UDP or Quick API to JavaScript. Why? Browsers do not allow raw UDP socket access, Quick socket access, system level networking control, changing MTU, sending keep alives, congestion control, setting NAT timers. All of this is inside the browser network stack, not in JavaScript. Quick is implemented in Chrome networking stack C++. That's why it's near to the hardware. Firefox networking Rust or C++. Safari networking C, OS kernel for UDP parts. User space, Quick libraries in servers C or C++, Rust or Go. Not in JS, not in React. How React, Angular, Next.js actually use Quick? They use Quick automatically because browsers use HTTP 3 automatically. When your front end calls fetch argument slash API slash user semicolon, the browser networking layer picks HTTP 3 Quick if server supports it, handles handshake, send Quick packets, manage idle timeout, detects PMTU, does keep alive plus retransmission. No JS touches it. What Quick code in React looks like? It looks like this. Const data equals await fetch argument code https :/example.com/video, and then closing parenthesis semicolon. That's it. No Quick API, no UDP, no handshake code. All Quick behavior is inside Chrome or Chromium networking stack, not your app. What Quick handshake logic looks like in real code: C++, Rust, Go. Below is a real pseudocode from Quick implementation like Quick, MS Quick, and GTCP2. Binding a UDP socket done by server, not front end. For Rust, let socket equal UDP socket : bind argument 0.0.0 : 443 dot unwrap function semicolon handling incoming Quick packets. Let mat buff equal argument 0 semicolon 2048, then let argument len comma addr equal socket dot rec v underscore from with an argument end mat buff closing parenthesis semicolon. Then let matcon equal quitch : accept with an argument con underscore id comma and mut config close parenthesis semicolon. Then con.receive with an argument and mat buff inside it len closing parenthesis question mark semicolon. Quick handshake while con dot is underscore incomplete inside it let out equal con dot send mat out underscore buff, then socket dot send underscore to with an argument out comma addr. Idle timeout configuration config dot set underscore max underscore idle underscore timeout with an argument 3000. PMTUD path MTU discovery config that enable underscore PMTUD argument true. Retransmission logic PTO if con dot timeout dot elapse inside this is con dot on slash timeout. Sending application data con dot stream underscore send argument 0 comma b quote hello world comma true semicolon. Why front end frameworks have nothing to do with this? React, Angular, Next, render HTML, manage UI components, handle routing, manage local state. They do not touch the network stack, control protocols, manage UDP sockets, control quick internals. They only call APIs like fetch function, XML, HTTP request, WebSockets, Web Transport, the only browser expose quick like API. The only web API that exposes quick like behavior Web Transport in HTTP 3Bs. Const transport equal new Web Transport argument https colon slash slash example.com colon 433. Then await transport dot ready semicolon, then const stream equal await transport dot create bidirectional stream function, then const writer equals stream dot writable dot get writer function, then writer dot write argument new uint 8 array argument 1 comma 2 comma 3. Even here, no UDP socket access, no MTU control, no timeout settings, no retransmission settings. The browser handles everything. Summary: 100% is Quick is 100% invisible to front-end code. Quick components, browser and server only. Quick feature, UDP socket bind, implemented by browser OS, available in React, no. Quick feature, handshake, implemented by browser or server, available in React, no. Not keep alives, implemented by browser or server, available in React, no. MTU or PMTUD, browser or server, available in React, no. Retransmission, PTO, browser or server, implemented by browser or server, available in React, no. Quick feature, congestion control, implemented by browser or server, available in React, no. Packet pacing, implemented by browser or server, available in React, no. Front-end, React, Angular, Next.js see none of these. They see only fetch, actions, WebSockets, Web Transport. So let's go back. We went on the statistics of how the TCP and UDP works. So some of these applications use a simultaneous while a connection is being set up or cleared, so that's the ideal. But one of the tricky problems for a TCP NAT is handling peer-to-peer applications operating on host, reading on private sites of multiple NATs, which has been solved by Stan, Turn, and Ice, which we will discuss in the next video. Some of these applications use a simultaneous open, whereby each end of the connection acts as a client and sends SYN packets more or less simultaneously. TCP is able to handle this case by responding with SYN plus ACK packets that complete the connection faster than with the three-way handshake, but many existing NATs do not handle it properly. RFC 5382 addresses this by requiring Rec2 that a NAT handle all valid TCP packet exchanges and simultaneous open in particular. Some peer-to-peer applications like network games use this behavior. In addition, RFC 5382 specifies that an inbound SYN for a connection about which the NAT knows nothing should be silently discarded. This can occur when a simultaneous open is attempted, but the external host SYN arrives at the NAT before the internal host SYN. Although this may seem unlikely, it can happen as a result of clock skew. For example, if the incoming external SYN is dropped, the internal SYN has time to establish a NAT mapping for the same connection represented by the external SYN. If no internal SYN is forthcoming in 6 seconds, the NAT may signal an error to the external host. Later, we will discuss how the mechanics of the most NATs with respect to how it actually maintains sessions, but not in UDP. Let's discuss this. UDP is somewhat different, however, because there are no connection establishment and clearing procedures as there are in TCP. More specifically, there are no indicators such as the SYN, FIN, and RST bits to indicate that a session is being created or destroyed. Furthermore, the participants in an association may not be completely clear. UDP does not use a 4-tuple to identify a connection like TCP. Instead, it can rely only on the two endpoint address or port number combinations. So it doesn't have those port tuple, therefore it must rely, or it only rely on two endpoints, address and port combination. To handle these issues, UDP NATs use a mapping timer to clear NAT state if a binding has not been used recently. So that's the 60 seconds to 2 minutes we have discussed. But remember, quick actually does a keep alive. There's a considerable variation in the values used for this timer to determine what recently means, but requires the timer to be at least 2 minutes and recommends that it be 5 minutes. A related consideration is when the timer should be considered refresh. So just with the TCP, there's also recommended behavior of 5 minutes and it requires 2 minutes. So a related consideration is when the timer should be considered refresh. Timers can be refreshed when packets travel from the inside to the outside of the NAT, outbound refresh behavior, or vice versa, not inbound refresh behavior. But again, most NAT only use outbound refresh. RFC 4787 requires not outbound refresh behavior to be true. Inbound behavior may or may not be true. As we discussed in Chapter 5 and we will see again in Chapter 10, UDP and IP packets can be fragmented. Fragmentations allow for a single IP packet to span multiple chunks, fragment, each of which is treated as independent datagram. However, because of the layering of UDP above IP, an IP fragment other than the first one does not contain the port number information needed but by NAPT to operate properly. This is also applied to TCP and ICP. Thus, in general, fragments cannot be handled properly by simple NATs or NAPTs. That's why quick and most of the things we have mentioned, even the application layer, avoid the fragmentation. Even in IPv6, fragmentation are unusual. So not in other transport protocols like DCCP and SCTP. Although TCP and UDP are by far the most widely used internet transport protocols, there are two other protocols for which NAT behaviors have been defined or are being defined. The Datagram Congestion Control Protocol, DCCP. It provides a congestion control datagram service. RFC 5597 gives NAT behavioral requirements with respect to DCCP. And RFC 5596 gives a modification to DCCP to support a TCP-like simultaneous open procedure for use with DCCP. The Stream Control Transmission Protocol, which I believe LiveKit have, provides a reliable message service that can accommodate hosts with multiple addresses. So if you have host and we want to contact with multiple addresses, kind of like a not with respect to how it communicate, kind of like multicast address, you can use this SCTP protocol, not an ICMP. ICMP provides status information about IP packets and can also be used for making certain measurements and gathering information about the state of the network. The NOT behavior requirements for ICMP are defined in RFC 5508. There are two issues involved when NOT is used for ICMP. ICMP has two categories of messages, informational and error. Error messages generally contain a partial or full copy of the IP packet that induce the error condition. So it has the record of the IP packets that actually did the error. They are sent from the point where an error was detected or from the time the error was detected. They have the timestamp, often in the middle of the network. So it records the router in the middle of the network that allowed that error to happen to the original sender. Ordinarily, This presents no difficulty, but when an ICMP error message passes through a NAT, the IP addresses in the included offending diagram need to be rewritten by the NAT in order for them to make sense to the end client called ICMP fix up. So if an ICMP error message passes through a NAT, the IP address actually or the offending datagram need to be rewritten by the NAT in order for them to make sense to the client called ICMP fix up. So it needs a rewritten because again, the basic of NAT is it needs to rewrite IPs. For informational messages, the same issues arise. But in this case, most message types are of a query or response or client server nature and include a query ID field instead of the normal protocol that is handled much like port numbers for TCP or UDP. Thus, a NAT handling these types of messages can recognize outgoing information requests and set a timer in anticipation of a returning response, and therefore a NAT that actually send this ICMP error that has query ID will set a timer anticipating that response. Instead of port number, it anticipate an error or query ID. NAT and tunneled packets. In some cases, tunneled packets, see chapter 3, are to be sent through a NAT. When this happens, not only must a NAT rewrite the IP header of that sending packet, but it may also have to rewrite the headers or payloads of other packets encapsulated within. One example of this is the generic routing encapsulation header used with point-to-point tunneling protocol (PPTP). When the GRE header is passed through a NAT, its call ID field could conflict with NATs or with other host tunneled connection. If the NAT fails to handle this mapping or this call ID with other connection or with encapsulated data, communication is not possible. As we might imagine, additional levels of encapsulation serve only to complicate a NAT jobs further. NAT and multicast. So far, we have discussed only unicast IP traffic with NATs. NATs can be configured to support multiple multicast traffic. See chapter 9, although this is rare. RFC 5135 given the requirements for handling multicast traffic through NAT. In effect, to support multicast traffic, a NAT is augmented with an IGMP proxy. See RFC 4605 and chapter 9. In addition, the destination IP address and port numbers of packets traveling from a host on the outside to the inside of the NAT are not modified. So in addition, the destination IP addresses and port numbers of packets traveling from a host on the outside to the outside of the NAT are not modified. For traffic flowing from inside to outside, the source address and port numbers may be modified according to the same behaviors as with unicast UDP. So for multicast, you're actually modifying from inside to outside, but from outside to inside it's not modified. You receive the same packet. So in order to do this, it must be augmented with an IGMP proxy, which we will discuss in the future videos. NAT and IPv6, and also this NAT and multicast is rare. To many protocols designers, NAT arose as a necessary but undesirable wart that has added a tremendous amount of complexity to the design of every other protocol. Consequently, there is a staunch resistance to supporting the use of NAT with IPv6 based on the idea that saving the address space is unnecessary with IPv6 and that other desirable NAT features like firewall-like functionality, topology hiding, and privacy can better achieve using local network protection (LNP). So it further complicates an IPv6 support LNP. LNP represents a collection of techniques with IPv6 that match or exceed the properties of NATs. Aside from its packet filtering properties, NATs support the coexistence of multiple address realms and thereby helps to avoid the problem of a site having to change its IP address when it switches ISPs. So NAT helps with preserving IP address. For example, RFC 4193 defines unique local IPv6 unicast addresses (ULAs) that could conceivably be used with an experimental version of IPv6 to IPv6 prefix translation called NPTv6. It uses an algorithm instead of a table, so instead of data structure, to translate IPv6 address to different IPv6 address, i.e. in different realms based on their prefix. As a result, does not require keeping per connection state as with conventional NAT. So as a result, they do not require keeping per connection state than conventional NAT if you use this IPv6 address to translate to another IPv6. But there's a disadvantage. So there's a pros and cons. That's its pro, but there's also a con that it does not preserve the limited address, like NAT. In addition, the algorithm modifies addresses in such a way that the resulting checksum computation for common transport protocols (TCP, UDP) remains the same. This significantly reduces the complexity of NAT because it does not have to modify the data in a packet beyond the network layer and does not require access to transport layer port numbers in order to operate properly. So another disadvantage is it doesn't rely on transport layer for checksum, because the algorithm works in such a way that the resulting checksum computation for common transport layers such as TCP or UDP remains the same, so no recalculation. However, applications that require access to a NAT's external address must still use a NAT traversal method or depend on the ALG. In addition, NPTv6 does not by itself offer the packet filtering capabilities of a firewall, so additional deployment consideration must be made.